You want to hit the light, somebody? All right, today we're going to talk about other methods of measuring dose, absorbed dose. And the references are TG69 that discusses radiographic film. Con chapter 8.9, Con just touches it on 8.9, covers it a little bit very, very quickly. We're going to go into more detail. And Pogorshak's got some references in sections 3, 4, 3, 5 through 6, and then ADEX has something in chapter 14. I believe that's the diodes, because we're going to be talking about several ways of measuring dose. So here's our outline. I thought I'd put an outline today because we're going to talk about so much. First, we're going to cover radiographic film, then GAFchromic film. There's a difference there, okay? And we'll be discussing the differences between those two. Then thermo-luminescent dosimeters, and then diodes, then MOSFETs. Then we're going to touch a little bit on freaky dosimetry and calorimetry, just so you guys know what that's about. Over the years, back in the day when I started, we only had radiographic film. Let me just adjust this. We only had radiographic film, and we had radiographic film and TLDs. We also had some diodes, not too many MOSFETs. So over time, GAFchromic film became a lot more prevalent, and so have diodes and MOSFETs. So there's a lot more to learn these days. Okay, so first, radiographic film. I might go a little quickly. Stop me if something I say doesn't make sense, okay? Because it might make sense in my head. So first of all, the anatomy of radiographic film. You folks have seen radiographic film, and that's the film that is exposed that we use in radiation therapy or in diagnostic radiology, and that's the older film. That's the film that has to be light tight because it's sensitive to ambient light, regular light. It has to be light tight, so it's either in a cassette, and I actually have a cassette in my office. I can go grab it during the break. It's either in a cassette or it's in what we call a ReadyPack envelope. And I don't know if you've seen ReadyPack envelopes. They're envelopes that are completely opaque and they don't let light come in. And it's used to be exposed with radiation and to give us an image. And so this is the structure of it. There's its structural base is a polyester film base, and it has nothing to do with image forming. It's just to create structure, to make it so you can hold it and it doesn't bend too easily. And that's 200 microns thick. It's 0.2 millimeters. And then on either side, this is called a double emulsion film because there's an emulsion on, which emulsion is like a gel that has something suspended in it. And the emulsion is coated on both sides of the space, and the emulsion is what contributes to the image forming process. This is what's involved in it. And then above the emulsion is a protective layer, half a micron, really thin, and that's just so you don't get emulsion on your hands and you don't spread this stuff all over, okay? So what's in the emulsion? Emulsion is, there's silver halide crystals in the emulsion. They're bromide crystals, and they're suspended in a gelatin, okay? And let's see. So here's what happens when this emulsion and the film is exposed to radiation. The electrons are captured at trapping centers in the crystal. Remember how electrons, we talked about electron trees, how electrons can be trapped in a polymer or in a crystal. Okay, so electron trees. Do you guys see the electron tree?
Where's the picture?
Oh, there's the picture. Okay, I have one in my office too. This, we irradiate acrylic, and the acrylic holds the charge, and then we can tap it with a nail that's attached to the ground, and all the electrons come out. Well, it's just an example of how electrons can get trapped in a polymer. They can also get trapped in trapping centers within a crystal. So electrons neutralize mobile silver ions in the halide grains. Okay, so there's silver ions inside those grains. So electrons can neutralize them, which means if they're positive, then these mobile electrons that are flowing in the crystal due to radiation, they'll neutralize the silver. Okay, so silver plus becomes neutral silver. So these minute deposits of metallic silver, and they appear black within the emulsion. Okay, so this positive silver is not black, but once it gets neutralized, it becomes dark. Each grain contains so each of those grains in that previous slide, these little grains I've got in that schematic, each grain contains about 10 to the 10 silver plus ions. And grains are about 1 to 2 microns in diameter, and their shapes can be cubes or tablets. I mean, they've done electron microscopy on them, and they look like cubes or tablets. When the film is developed, those grains can contain a few silver atoms, and those will become metallic. Others would get washed away. So after they get irradiated, the film goes through a developer, and we'll talk about the developing cycle. And the ones that have at least 4 have converted the silver plus to silver. At least 4 will stay. So if 3 get converted, they won't stay, they'll get washed away. 2 get converted, they'll get washed away. You need 4 to make that clump that'll stay on the film. I mean, that's 4 out of 10 to the 10, that's very few. So you don't need much. The purpose of the base is to give the film structural support, as well as to reduce some light transmission. So if you just take a film and you don't irradiate it, and you run it through the processor, it comes out, it looks blue, like a light hint of blue. That's because all the emulsion has been washed away, and all you have is the structural layer. But why is it blue and not clear? It's blue because when you hang it on a light box, if it was completely clear, there'd be too much contrast. And that's harder to read for radiologists. That's harder to read than a film that has less contrast. So over the years, that was just a preference of radiologists, that they'd like to reduce the areas where there's no radiation. They'd like to keep that a little bit blue, a little darker than just clear. So here's the processing. Have you guys seen a processor in IROC? There's a lot of signal processor. No, you know.
I've worked with film before, but
Okay.
I don't know if it's any different from developing 9mm film compared to.
It's exactly the same.
Okay.
Yeah, it's exactly the same. A developer, film is film. There's silver Holly grains. It's the same stuff. The material in the emulsion is a little different from film to film. There's Kodak and there's Fuji, and they make different kinds of films. And the differences are that the film is sensitive to, some of them will be sensitive to green light, and some of them will be sensitive to another frequency, maybe blue light. And so that's the differences between the film. Why do you think that, you know, in those movies where somebody walks into a processing room, why is the light red? The light is always red. You notice that?
Is the film not sensitive to that?
It's not sensitive to red. So film is made so that it's not sensitive to red light, and they're usually sensitive to green. Okay? Although there's always a little bit of film fog. Film fog is due to some light that creeps in under the door or that kind of thing. So, but anyway, getting back to the processor. A processor in general, the modern processors, they're usually quite large. They made a few tabletop versions of it, but they're usually quite large, and they're large because it has to hold these chemicals in baths. So the first chemical that the film is exposed to is the developer, and so the developing stage, it's a chemical, it's in a container, and the film goes in, and there's usually some automated wheels that push the film through this bath. Okay, the rollers are tight and they hold the film. They run their film through the rollers, and the rollers push the film through this developing bath, and it adds electrons to convert more silver ions near the converted ones. So say there's already some silver ions there, neutral silver ions. The developer adds more electrons. So it's a chemical that has a lot of electron donors. You know, some elements have a lot of electron donors in the valence shell. Well, this one has a lot of electron donors, so it creates a snowball effect. So where there's a little bit of silver, it creates a lot more silver, and then it creates that little spot, makes it bigger. We're talking microscopic scale now. If the development is too long, so if it spends too much time in that bath, it becomes too dark. The film gets too dark, and you lose all the contrast. After that, the film goes through more rollers, and as it's moving through the rollers, and the rollers are turning, they're motorized, then it goes into the fixing stop bath. So the fixer stops that process. Because if the process goes on, the film will just get all dark. So it stops the development process to avoid overdevelopment and fogging. Also removes, oh, there should be a bullet here. Also removes underdeveloped grains. Okay, so the grains, remember how I said that if you have 3 grains, it's not going to develop. So the fixer gets rid of all those. And then when you walk into a processing room, it smells like vinegar. And that's the fixer. The fixer smells like vinegar. There's acetic acid in it. So then after that, so now the film's got all these chemicals, you don't want to get this on your hand, right? So then it goes into the wash. So it takes a little bath. The film goes in, it takes a little bath. And water is used to clean out the fixer solution. And then it gets dry. There's a blower and it dries the film. So when it comes out, it's not wet, it's just a little warm when the film comes out. and you won't get chemicals on you. Okay, and then the speed with which it goes from here to here is very important, because the time it's spent on the developer is going to affect the darkness, and the time it spends in the fixer is going to affect the darkness. And also the temperature is important too. If I remember correctly, it's around 35 degrees Celsius that it has to be at. Because that will affect, the temperature will affect the darkness of the film as well. Okay, now, so that's film. I just went through that quickly because we don't use film today, but you guys have to know how that works, how film works. Okay, optical density. So now, for us, we're not radiologists. We're not going to put up a film in a light box and make a diagnosis. We're going to use film for dosimetric purposes. So for dosimetric purposes, we need the quantitative data. Okay, so one parameter that gives us quantitative data about the film is OD, optical density. Why does it beep every time I do that? Optical density. I don't know why it beeps. Optical density, and that refers to the degree of film blackening. And so, how do we measure optical density? First of all, the darker the film, the higher the optical density. We better go. All right, guys, we got to get out. All right, fire alarm over. Everyone's safe. That was just a drill.
Pretty long drill.
Yeah, I know. Okay. All right, let's get back to optical density. So, optical density. So how are we going to measure the darkness of the film quantitatively? We need to get a number. Obviously, we can look at it and say this area is dark, this area is light, but we need to quantify that. So we do that by using a densitometer. We measure light with a light. We measure optical density with a light source and a light detector. So the film is placed between a light source of intensity I0 and then a light detector. Okay? And that's a detector that detects intensity of transmitted light. So some definitions. Transmission is equal to IT, and IT is the intensity of light that the detector measures, and divided by I0. So that's the transmission. Okay? So that makes sense. It's how much light is transmitted divided by how much it originates from the light source. And then the opacity is just the inverse of that. Okay? It's 1 over the transmission. And optical density itself is log of I0 over IT. And the reason we use log is because there's a huge range. It's like tens of thousands of degrees. Yeah.
Just to make sure this is log-based 10, right?
It's log-based 10.
Okay.
Yep. Yeah, I always write, if it's log-based E, I write ln.
Okay.
I know some books are confusing. They'll write log and then it's log-based E, yeah. So it's base 10, so let's go on. So the sensitometric curve. Now, different films will respond differently to radiation. And their response is characterized by the sensitometric curve. And I'll explain how that works. The sensitometric curve relates optical density to dose. Okay, so in the previous slide, we showed how we measure optical density. We're still not at dose. So we need something to convert optical density to dose. That's where this curve comes in. Optical density is not linear with respect to dose. It follows a relationship described by the film sensitometric curve. So if I measure an optical density of 10, and that relates to a dose of 10 centigrade, if I measure an optical density of 100, that doesn't necessarily mean it's 100 centigrade. Okay, it's not linear. It's a nonlinear response. So to get dose information from film, we must apply all optical densities on the film to a sensitometric curve. And this is usually done empirically. In other words, we take these measurements. We measure these curves ourselves. And the shape of the curve depends on the film type, what kind of film you're using, the radiation type, 6 MeV electrons versus 12 MeV versus 6 MeV photons versus cobalt-60 radiation type, and then the processing. Also, the processor affects the sensitometric curve. Okay, the processing time. Actually, from processor to processor, you might get different sensitometric curves. We'll go into that. Yeah. So this is just a little picture, a big picture on the next slide. Okay, so how do we measure this? And the way we do this is how and why and when. Okay, so why, we know why, because we want to convert optical density that we measure on the film to a value of dose. Okay, that's why we did the sensitometric curve. How do we measure it? We take, here's how I do it. People do it different ways. What I do is I take a piece of film that I'm going to use, where I want to characterize it, and I cut it up into little squares. Okay, and then I write on each square, I write how much dose I'm going to give to that square. So I have 10 centigrade, 30 centigrade, 50 centigrade, through a range of doses that are going to be clinically relevant to me, maybe all the way up to 1,000 centigrade. So I have little that I've labeled. And then I go into the linac room and I place a piece of film on some buildup, and then I set a 10 by 10 field, and I can place it at Dmax, and then I know if I deliver 100 monitor units that the film's going to get 100 centigrade. Okay, so I put it in a known configuration. So then I deliver the known dose to these films. Then I measure the optical density, and I just plot it. So I plot the optical density I measure on the little square versus the dose that I delivered. And that's a known dose because I'm using a calibrated linear accelerator. Okay, and then I plot it, and I get something that looks like that. Okay, characteristic curve. And then, so with this, so now I have a characteristic curve for this film and the processor that I'm using. Okay, so film processor and energy. So I might want to repeat this for 10 MV, 18 MV, etc., and look at the curves. And as it turns out, what I've seen that over all the energies, photon energies, the curves look very similar for the films. Okay, so I don't find there's much energy dependence, but it's just still a good idea to do it on your own when you're going to be in the clinic. In other words, to look at the different energies. Okay, so now we've got, so now for this film in the processor, you have a curve that relates optical density to dose. Now, some terminology, the gamma of the film corresponds to the slope of the straight portion of the curve. So gamma is just the slope of the straight portion of that curve. Okay, the latitude corresponds to the range of dose a film can cover. So a long latitude can withstand high doses before it saturates. So a film with long latitude, you can, this straight portion is going to, the slope is going to decline. In other words, the slope is going to get smaller, and which means that this film can cover a wider range of dose. A short latitude, the slope is steeper, and the straight line portion becomes a very narrow band within the dose. Okay, so you don't, by the way, you don't want to use this film in these areas here. Okay, so in these dose regions, I can't do two at a time. In these, you don't want to use this. Why do you think you don't want to use it in those areas? Right. Why is that? Why do you think that is? Look at that. Look at the shoulder, for example, or up here where it saturates. What happens if you if you deliver, say this is 800 centigrade over here, and then there's 1,000 over here. Centigrade. Correct. A very small difference in optical density, and so your sensitivity and measurement is it's not going to be as sensitive when you measure it here compared to a difference of 200 here. If we look at the same, okay, much more sensitive. So your signal to noise ratio is a lot better here than it is up here. So we want to stay in the straight line portion. We want to stay in this gamma portion, the straight line portion of the film. The speed, another term, speed of the film. And that is just intuitively what speed means is a film that's very fast doesn't require a lot of dose to get dark, to get a certain darkness. The speed that's slow requires more dose for the same darkness. And that's speed. So a fast film will get dark with very little dose. And speed, the definition of speed is 1 divided by the dose required to produce an optical density of 1. It's 1 over that. Okay. So the dose required to produce an optical density of 1, say the OD of 1 is, let's see, how do I clear the whole screen? I'm not sure how to clear the whole screen. Clear drawing? Yeah, okay. So, optical, say 1 is right here. Okay, so whatever dose this is, say it's 80 centigrade. Okay, so this is optical density of 1.0. Okay, at 80 centigrade. So the speed of the film is 1 divided by 80 centigrade. So, quick question. Three characteristic curves, and the question is, which film has the greatest latitude in color? Green one does, okay? Because it has a longer range over which you can measure dose. And which film has the greatest speed? This one? So we're talking about optical density of 1. Yeah, this one here, this is the fastest one because it requires the least amount of dose to get an optical density of 1. And if you take, say this is 50, 1 over 50 is going to be greater than, say this one here is 100, 1 over 50 is going to be greater than 1 over 100. Okay, pop question, which film has the greatest base and fog? Oh, did I talk about base and fog? Okay, ask you a question about that. Base and fog. Oh, here, base and fog. So base and fog in any characteristic curve in any film, you'll always have some inherent darkness in the film, even if you don't irradiate it. Even if you take a film and you run it through the processor. Remember that ambient light in the processing room that's going to darken the film. The processor itself, in the development stage, there's always some chemical that's left behind, so that contributes to base and fog. Film fog is exactly what I just said. Ambient light, some development caused by the developer, and those are the two main ones. The base is the polyester base. Remember how it's not completely transparent? There's a little bit of darkness to it. That's what base is. So the base and fog corresponds to this tail right here. So it's never, optical density is never 0 with film. Okay, there's always a little bit there. That's base and fog. So which one has the highest base and fog? The greatest base and fog. Right. Yeah, the red one is. Okay, where is film used in radiation therapy? So where do we use film? Quality assurance of accelerators to measure flatness. Remember flatness and symmetry, we measure that with chambers. Well, we can also measure it with film. We can lay a piece of film flat on the table and irradiate it and scan through the film and measure flatness and symmetry. We can also use it to measure radiation versus light field. Have you guys done that, by the way, in IROC?
Yeah.
Radiation versus light field. Do you use that orange stuff?
Yeah.
The GAFchromic? Okay. So that's radiation versus light field. And then 2D dosimeters provides a map of intensity distribution which can be converted to dose. So a film is a two-dimensional dosimeter, and which the darkness, after you scan it, the film, the two-dimensional dosimeter, you can convert it to dose with the H and D. An H and D curve is the same as the characteristic curve. Those are the two fellows who came up with it, Herder and Driftfield. Okay, and here's some examples of how we use film. There's the radiation versus light field. Remember, you lay the film down, project the light field on it, and you draw these lines that indicate the edges of the light field. Then you leave the room, you radiate it, and you compare the radiation versus the light field. And collimator star shot, that's another. Have you focused on that?
Yeah.
Okay. So that's another example where you can use film. Okay. Then here's another pseudo-dosimeter. This is an IMRT intensity pattern. Okay. So IMRT is a way that we treat our patients where the intensity varies over the field. And if we want to check it, you can lay the film down and irradiate it with the machine, and then scan that and compare it to what we expect from the treatment planning computer. Okay, so the different types. We're still talking about radiographic film. The different types are, number one is Kodak XV. This is it's called XV. The V stands for verification film, X is X-ray. And then this one saturates at 100 centigrade. Okay, so you can't deliver too much dose to this one. XV is energy dependent. Okay, so you're going to get a different response for low energy photons than you are for high energy photons. In other words, response meaning darkness. It used to be most common film for dosimetry, and it's pretty cheap. And then came EDR film, and EDR stands for extended dose range. The big advantage here was this 800 centigrade saturation point, so you could deliver a lot more dose. So is this film faster or slower than XV? Slower, okay, so it needs a lot more dose. The big advantage here was when IMRT came around, like in 2002, around 2002, we needed to check our IMRT patterns, and we were using film. So if we used XV and it's saturated at 100 centigrade, if we were doing a film where we wanted to look at the composite distribution, how much do we treat our patients with on a daily basis? Regularly. What's a typical dose we treat our patients with? Are you guys see that any got through any charts and looked at doses and prescriptions? Does 180 centigrade A sound familiar? Well, 180 or 200 is what we typically treat our patients with on a daily basis. So if we're checking this IMRT film and it is saturated at 100, yet we have a 200 centigrade A or 180, it's going to saturate. Okay, so that film was not useful for IMRT. So this came out. This was very timely. This is where this film came out. Came out around the same time as IMRT, and it probably was developed because of IMRT. It's almost energy dependent. Now, what makes XV film energy dependent? What do you think? What makes something energy dependent? Remember we talked about chambers energy dependence? What makes something energy dependent?
What it's made out of.
Yeah, what it's made out of? Could be geometry. The atomic number. Remember how it's something that has a high atomic number is going to be the energy, the dependence in the signal is going to shoot up at low energies because photoelectric effect is proportional to Z cubed. Okay, that's why. So Kodak XV film has silver. Remember, it has silver in it, and silver, the K edge of silver, K edge is about, it's about 25, I'm just going to say 25 kDV, somewhere around there. Okay, so here we've got silver, which has a very high Z, and a K edge of 25 kV. So this is energy dependent because as you're rating any material, even though you're using 6 MV photons, you're creating scatter. Remember Compton effect? Scatter, that scattered energy could be anything. It could be zero, it could be from 0 all the way up to 6 MV. So we do have a component of that, the scattered photons that are 25 keV. So those guys are going to be completely attenuated by the film, and not completely. They'll be preferentially attenuated by the film. So all those low 25 keV photons are going to get absorbed by the film. That causes an energy dependence. Okay, so we'll go back to EDR. So EDR doesn't have as much silver. It has less silver. So it's almost energy dependent. It's more expensive, and it was available since 2000. So XV energy dependence. So XV film is photon energy dependent because of the K edge of silver. Low energy electrons that are produced in the medium have a very high cross-section probability of interaction due to the K edge. That's what I just said. EDR film has much fewer silver atoms. Okay, I just said all those things. Okay, so here's an example of the energy of what happens, or here's an example of the effect of the energy dependence. This is a block of solid water material. It's white, and then this is the film seen on edge. Okay, and this is XV film. Okay, and then X-rays are being shot in this direction. And then once we take this film and we scan it, we can scan a PDD, right? Because the PDD starts here, and if we scan in this direction, we can get a PDD curve from our film. So here's what the PDD curve looks in chamber, with a chamber in water, it looks like this. And then if we overlay the optical density converted to dose from the XV film, it looks like that. It looks a lot higher. It looks higher because of the energy dependence. Okay. So basically, the film is darker. That's what it's telling you. The film becomes darker for a certain depth. The XV film will be darker, and it'll be darker because of this K edge, because of this extra absorption that is going on at low energy, from the low energy photons. So pros and cons of radiographic film. Pros: spatial resolution, 1 micron, great resolution. It's possible to film. This allows spatial accurate isodose distributions that can be visualized, and it's also permanent record. And once you irradiate it, you can store it and you can always rescan it. Disadvantages: wet chemical processing is fraught with problems such as flow rates, temperature fluctuations, which can affect darkness, and energy dependence for X-rays with XP. So the process is a big problem with film. Because processors, depending on when you turn it on, for example, back in the day when we were using film constantly for verifying our patients' positions, the processor was running constantly. And the replenishing rate was pretty constant over the day. Once you first turn it on, it takes a little while to warm up. You run a few films through it, then it's operating fine. And so back in the day, we were using processors for dosimetry, film and processors for dosimetry, and they were okay. But then, after we started getting pore imagers on our Linux, we stopped using film. Okay? And we would use film when the pore imager was down, or I don't know, for verification during treatment. I don't know. We were using film, but very, very seldom. So what would happen is that the processor would get turned on, and then they wouldn't run too many films. So the rollers would get clogged up because they weren't constantly moving. The temperature fluctuation would change. So for dosimetry purposes, those processors were not good. So those are processor issues. Then comes along radiochromic film. Now, radiochromic film is different than radiographic film. There's no silver halide. There's no silver crystals. It's a dye. Okay? It's a dye, something that turns color. It turns color with the amount of radiation. So the darkness of the film is still proportional to the radiation, to the amount of radiation. But it doesn't work in the same way. You're not converting silver plus ions to silver atoms. You are just changing the color. It's a dye. It's like food coloring. Okay, so properties of radiochromic radiographic film. Radiochromic GAFchromic film. Huge dynamic range. They can make these films respond in those ranges. Don't need to process it. Great, that's awesome. Okay, because our processors weren't being used anymore. Insensitive to visible light. Okay, so it's sort of insensitive. It's still not a good idea to leave them out, but it's insensitive to visible light for the most part. High spatial resolution. Again, it's filmed very, very small pixels. There's no energy dependence. Almost tissue equivalent. So the effective Z is 6 to 6.5. Tissue is around 7.5. Used to be expensive, but they're getting a little cheaper because more and more people use them, and so the manufactured process is better. And then there's a guidance document, TG55 for radiochromic film. And then the manufacturer has a website. There's tons of information on that website. It's a great website. Okay, so the different types of, I'm going to go into the different types of radiochromic film. RTQA, that's the film that you guys use for radiation versus light field. That film is opaque. You can't see through it, right? It's called reflective. So that you need light to shine on it, and you see what reflects off it. It's not transmitted. It doesn't transmit. You're not going to use it for scanning like you would when you're measuring optical density, because you can't shine light through it. Okay, so it's used mostly for qualitative purposes. It's a 3-layer film. There's a substrate that's 97 microns. Let's see, which is a clear orange polyester layer. Then the active layer is 17 microns, and then there's a base, 97 microns, and it's opaque, like I just said. And the range for RTQA is 2 to 800 centigrade. This is similar to the EDR film. The EDR was on up to 800. The price is pretty cheap, $7 per sheet, per 10 by 10 sheet. It's probably cheaper now. This is an old price. The main use is for qualitative QA. Qualitative meaning something that you're just going to look at and you're going to evaluate qualitatively. Like light versus radiation field, would you say that's qualitative or quantitative?
Well,
qualitative?
Yeah.
It's actually quantitative.
really?
Yeah, because you have a tolerance, right? You have a tolerance for what the passing criteria is for light versus radiation.
Like when we did it, we just looked at it, we didn't measure it.
I know, but it is sort of quantitative. And I mean it's quantitative because your tolerance based on a protocol that sets tolerances for JAWs. Your tolerance for the JAW is 2 millimeters on a sign. Okay, so your light versus radiation field coincidence should be within 2 millimeters. So it is quantitative from that respect, because you should, if it looks like it's more than 2 millimeters, you should take a ruler and verify that. So that's the quantitative. But usually you can tell whether it's within 2 millimeters, because 2 millimeters is actually quite big to the eye, and you can easily see something that's within 2 millimeters. So main use is qualitative. Yes and no. Qualitative QA. It's not that quantitative. In other words, we're not going to put it through a scanner and measure quantitative data. Okay. We also use our TQA film for star shots. You can also use it for a star shot. That star pattern on. Have you guys done a star shot?
We did it with just paper.
You did it with paper?
Yeah.
Okay. You can do it with paper. That's fine too, for spot checks. But you can also irradiate by closing the jaws down. And you can irradiate the film and show a spoke pattern. And then you take a thin pen and you draw lines right in the middle of the dark bands. And then you look at where they coincide in the middle. And then you apply the same criteria as you would with the paper test that you do. So you could do that test too. Uniformity is not ideal. It's not a very uniform film. Okay, and here's the characteristic curve of our TQA film. And you see there's no basin fog down here, it just goes down to 0 because there's no processing, so there's no, and this is reflective too, so it's a little different. And the way they measure this is, here's the net visual, notice how they don't call it optical density, they call it visual density, because optical density refers to any films that are transparent. So visual density, and that just means how dark it is, and they measure that with a flatbed scanner. So you can put it on a flatbed scanner and scan it. In the flatbed scanner, you could set region of interest and measure the darkness, okay, based on your image. Okay, so that's what that looks like. So, and that visual density, and they've just defined 1 to be whatever, who knows what 1 is. There's no true definition. I mean, you can go into their document and see how they define it, but there's no standard definition like there is for optical density. Okay, then another kind of film is EBT film. This one is transparent. Okay, this is a much better film for quantitative measurements. Range 1 to 8,000 centigrade. EBT is made by laminating 2 film coatings, each having an active layer approximately 17 microns thick and a surface layer of 3. Okay, transparent. This is the polyester. This is the same thickness as before for the polyester base. Okay. The product is formed by laminating the 2 pieces of coated film by a proprietary technique requiring no intermediate adhesive layer, and it's transparent. So we can scan this now with the same kind of scanner we're using for the radiographic film, like the VIDAR scanner. Have you folks seen a VIDAR scanner? We have one. We have one in our treatment planning lab. It's a scanner where you'll drop the film in, and I'll show you those pictures of it. And you shine light through it, and on the other side, there are light detectors. Okay, so here's the scanner. EBT technique. So the EBT film, there it is. It's what you're seeing in this picture is the scanner. Here's the VIDAR scanner. And the scanner is composed of a fluorescent tube. You know, like the tubes that you have up here in a room, the regular fluorescent discharge tubes. And then behind the film is a row of detectors. Okay? And so the row of detectors is just one row, and and the distance between the detectors is 86 microns. Really, that's a really small difference, isn't it? So it's going to provide you great resolution. Okay, so. Oh, by the way, our VIDAR scanner at Evanston Hospital broke down one time. And, okay, we'll call VIDAR and find out what the quote is. The quote was like something like ridiculous, like $2,000 or $3,000 to get it fixed. So forget it. We called our biomedical engineering guys. We took this thing apart. So we opened it up, and we realized there was a tube, and it looked like, just like I said, it looked like one of these fluorescent tubes in a room. And the biomed guy says, "Oh, let me look this up." He found it for like $6, this tube. So he got a tube for $6. There was one difference. There was some silver tape wrapped around one end, and I think that silver tape was there so the light doesn't shine around the side, around behind, doesn't create any scatter light. So he bought some silver tape, put it on there. We plugged it in, and it was fine. So we fixed our VIDAR scanner. We saved $2,000 by getting a $6 tube. So anyway, that's how it works. It shines light through, and we measure the darkness. The film, by the way, is this blue. The EBT is this blue area. This other part right here is a protective, just a transparent protective layer that we put on there. So we don't get any gunk that's inside the scan onto the film. Okay, so now the EBT film, it's very technique based. You've got to know some things about it before you use it. It's directional dependent. So if you scan it, this is a landscape scan right now. Okay, but if I take it and turn it over a portrait, I'll get a different response. It'll be darker in one direction than it is in the other. And the reason is because of the way they make this film. This film is made by, there's lines of dye that are put in, and they're put in one direction. Okay, so if you scan it, if the light shines through, it's kind of like a polarizer. You know how a polarizer works? Okay, so a polarizer lets in light that's in a certain direction, that's moving in a certain direction, and it cuts out all the light in the other direction. That's why it reduces glare. When you use polarized sunglasses, it reduces your glare because it cuts out the light that's coming from a different angle. This film is kind of like a polarizing filter. So if you scan in one direction, the light is the scattered light is not going to get through, but it is going to get through in the other direction. Okay, so in one direction it's darker than in the other direction. Very important. So scan is directional. So your your characteristic curves have to be scanned in the same direction. So remember those little squares I was talking about that I write the dose on? I put a little arrow on those. Okay, so as I'm cutting this, I'm putting a little arrow that tells me which direction they're in. So I have to scan them in the proper direction. Then, front-back dependence. Whether you scan it in one direction, you're going to get difference than in the other direction. So when you open the box, and you take the film, start taking the films on, scattering them around, because the front, you're going to have to remember which way is front and which way is back, based on how they're packed in the box. Okay. Then post-irradiation darkening. See, there's a lot of issues with this film. But if you use the proper technique, it's a good film. After you irradiate it, it will, if we plot a graph of time and darkness, I'm not going to call, okay, I can call it OD. I wish I would stop. I'll just turn the volume down. So time, I'm going to call it OD, because it is an optical density now, optical density. There is let's see, it goes like this. I think the curve looks something like that. Okay, and the 2-hour mark, right around here, 2 hour, that's when it saturates. But it's still, after you irradiate it, it still gets dark. So if I scan my film right after I irradiate it, and then I scan it 2 hours later, I'm going to get a different result. Okay, so what that means that you've got to have a time frame for the film. You've got to say, I will scan this film at the 2-hour mark all the time, every time, for my characteristic curve as well as for my dosimetry measurements. You can pick 2 hours is a good time because that's when it starts to saturate. It's a little bit of gets in the way sometimes, because sometimes you would just want to get the work done. You don't want to wait. So, but you do have to wait for this one. And then here's the H+D curve for EBT film. Another thing about this film is that it's more sensitive to red light than it is to high light. So some people buy those fluorescent tubes. They buy them red. They buy red fluorescent tubes, and they get this is a better H+D curve because for the same change in dose, you get a bigger difference. You get a bigger difference in optical density for the same change in dose. So this is a little bit better. This red light. Okay. Any questions about that? EBT, pretty quick. So let's move on to TLDs. The TLDs have been around for a really long time. There's all kinds of studies done. So we really understand how TLDs work. There's a lot of material for you guys to learn about. So TLDs are an integrating dosimeter. By the way, is film an integrating dosimeter? Yes, it is. The more radiation you deliver, it's just going to add up. It's not measuring rate. It's not measuring radiation rate. Like an ion chamber can measure rate, right? Because you can measure current, and that's rate. So TLDs and films, those are integrating. The more radiation you deliver to it, it'll just keep adding up. Mostly used for in vivo dosimetry, which means that it's used to put on patients to measure the dose on the patient. They're made of they're crystals. you seen them, by the way? You have seen them? Does Alexian have them?
Yeah.
You have seen them?
Yeah, very small.
They're really tiny. Yeah, they're 1 millimeter, 0.9 by 0.9 by 0.3 millimeters. Okay, they're usually little. They're usually little tablets. Okay, so they're 0.9 by 0.9 by 0.3 millimeters. I've actually used even some clones. I've used like 0.3 by 0.3 by 0.3 little tiny chips. They look like little salt grains. And I use them because I wanted to get better resolution for something I was measuring. Those are almost impossible to use. Okay, so usually measured for in vivo patient dosimetry, lithium fluoride. Oh wait, I got those dimensions wrong. 3 by 3. Oh yeah, 3 by 3. Sorry. Take it back. That did seem awfully small. 3 by 3 by 0.9 millimeters. Okay. Let's see how. Those are the most common crystal forms. Impurities in the crystal trap electrons during irradiation. Okay, so there's, a crystal is made of atoms, obviously, and the atoms, between the atoms, the way the atoms bond, well, between the atoms there are energy bands between the atoms where electrons can get trapped in these energy bands. And so impurities create these trapping centers for electrons, just kind of as a qualitative explanation. After irradiation, they're read out by heating and measuring the light output that they emit. Okay, so you irradiate the TLD, and then the amount of radiation that you deliver to the TLD is proportional to how much light that they'll emit after when you heat them up. Okay, some properties. Effective C is close to tissue. Okay, 0.2 versus 7, so that's great. Energy dependence at low energies. So there's a 25% energy dependence at 30 keV, which is kind of low. For us, for radiation therapy, it doesn't really affect us. The temperature of the main glow peak, and I'll talk about glow peaks in a minute, is 195 degrees C. Remember FMED? FMED for cobalt-60 is 0.809, which means that, what do we use FMED for? To convert something to something. Convert Roentgens to Roentgens to rats. Okay, so you take the number of Roentgens times FMED and you get rats. Okay, and FMED was 0.873 times mu absorbed over rho ratio between material and air. Okay, so if we have a radiation field of 1 Roentgen per minute, then the dose that a TLD would receive would be 0.809 rad per minute. Okay. Fade over time. Over 12 weeks, it'll fade about 5%, which gives you plenty of time to read them on. Not sensitive to ambient light. Light output is linear with dose up to 1,000 centigrade, so that's fine with us because we tend not to use doses that high, at which it becomes superlinear. And so after 1,000 centigrade, it becomes superlinear, which means it departs from linearity. Okay, so how do these work? So this is if you were to get down to the atomic level of what's happening inside the crystal. This is what it looks like. Okay, so this is the area of the valence band. This is the forbidden band between these two lines. And the valence band of the atom is down here. The valence band is the outer shell, right? So there's the valence band. And this is the forbidden band. So this is the area between atoms. Okay, and there are trapping centers due to some impurities in the crystal. Okay, there's a trapping center here, with a trapping center here, where electrons can drop in and get trapped. Okay. They're not mobile. Okay, so when the crystal is irradiated, electrons are set in motion. Okay, so electrons are set in motion, and they travel in the conduction band. That's where they're not trapped. That's where there's not enough attraction that they can get stopped. When they lose enough energy, they can now get attracted. Then they'll be attracted to the atom, and they'll drop down into the valence band. and then they get trapped, and they sit there. If the radiation continues, they might have enough energy to jump out and travel in a conduction band and drop back in. Okay, so once the radiation stops, there's nothing in the conduction band. There's no electrons moving around, and all the electrons that have been released have gone to trapping centers. And the more radiation there is, the more electrons are released, and the more electrons end up in these trapping centers. Okay, so let's see. So what happens when ionizing event by radiation? Okay. So then, when we apply light, we can apply light to this. When we apply heat, when we apply heat to the TLD, heat is energy, right? And so heat has enough energy to pull some of these electrons out of their trapping centers, make them go back into the conduction band, but they're not going to travel very far because they're not being irradiated. So pretty soon they'll drop back down, and they'll drop back down to a lower energy state. And as they do that, they emit light. Okay, and that light we measure. So the first process: radiate, create loose electrons. The electrons get trapped. The more radiation there is, the more electrons you're releasing, the more get trapped. Second part: heat them up, pull them out of these trapping centers, and as they come out of the trapping centers and drop back down to lower energy states, then they emit light as they do that. Okay, so if we're heating them, the nice thing about the heat is that as they get heated, they come out of these. The binding energy of these trapping centers is less than the binding energy of the lower states. Okay, so the heat that we apply has got enough energy to pull them out of here because the binding energy is low. And then when they get trapped in these, they're deeper, and the energy can't pull them out. The heat can't pull them out, and they're stuck there. So if you think about what's happening, you've got all these electrons in trapping centers with a low binding energy. You're heating them up, you're taking them out, and now where are they going? Well, they're not going to disappear. Okay, they have to go somewhere. And so they go down to the deeper, the K shell, the L shell, the F shell, the lower shells. Okay, so and then once they're in those lower shells, the heat's not going to pull out of it. Okay, so it's not like you've got electrons flying around and creating light as you're heating them. Eventually, they drop down to energy states where they can't get pulled out of. Okay. Well, this is a bad slide because it's kind of dark. But anyway, as we're heating these TLDs, as we're heating the TLDs, here's a little schematic. So the TLDs go into the TLD reader. Okay? And the TLD reader is a box, and all it has is a drawer in it. You open up the drawer, you put the chip inside the drawer, and the chip sits on what we call a planchet. That's what this is. Here's the planchet or the heater. Okay? So we put that on the metal planchet, we close the drawer, and we hit read with a button on it. It's very simple. You hit read, and then that planchet starts getting hot, and here's the temperature of the planchet. Okay, so in time, the temperature increases. Okay, and as the temperature is increasing, we're measuring the light that's coming off the chip. Okay, and we're not measuring integrating, we're measuring current. So we're measuring the rate of the light. So the rate that the light comes out increases, hits a peak, comes down, increases as the temperature goes up, increases, hits a peak, and then these are all peaks. This is a peak, this is a peak, but they're all meshed together. These peaks correspond to the different levels, to the different energies, trapping. Okay, so the peaks at the low temperature ranges are the peaks here near the conduction band. The peaks at the higher temperature are down lower. Okay, it takes more heat to pull them out, but there's more of them. Okay? There's more of these guys down here near the valence band, more trapping centers, or more electrons that get trapped in there than there are these guys. That's why the peak's so low. So as the temperature goes up, the peak gets higher. It also gets higher because you're releasing a lot more. So you're releasing some over here as you hit a peak, but as you're going as you're going through, you're still releasing some of these low energy ones. So they kind of add up. Okay, so anyway, the heater heats the TLDs, and then there's a device called a photomultiplier tube, which converts light intensity into current. Okay? And each peak represents a trapping energy level. I just said that. Higher temperature peaks represent energy levels that are closer to the nucleus. Yeah, I just said that too. Now, photomultiplier, we're going to talk about that.
You don't have these on site, right? The TLD readers?
Yeah, they're on site. They're always on site.
I thought they had to be mailed out for the TLD.
They can be. They can be. There's a surface where there's a service that you can mail out TLDs. But most places have them on site. Yeah. And the TLD reader, by the way, is hooked up to a computer. And the computer, so when you hit read, the computer plots the glow curve of your chip. Okay. So now you've got this glow curve. Now, that glow curve I showed you is not an ideal glow curve. I just showed you that so you could see the different peaks. But ideally, for the same chip, these peaks are not, especially the low temperature peaks, they're not very reproducible for the same peak, for the same chip. So what you want is a curve that looks a curve where you're just looking at the central peak. And there's a way of doing that. There's a way of achieving that because that makes it clean. What you're looking for, by the way, is the light output, remember, is current. But what you're going to do after you read the chip is you're going to measure the area under the curve. That area is proportional to dose. Okay? So that's what you're measuring. So if the area under the curve is not reproducible, then your dose is not going to be reproducible. So the way you get this single peak is through good pre-irradiation annealing. Yeah, oh, that's much better, thanks. Good pre-irradiation annealing, and it also eliminates these low temperature peaks, which are unreliable. Okay, and here's pre-irradiation annealing. So the chips, before you use the chips, they have to be, this is what you have to do. You have to prepare them. There's a preparation process. And first you heat the chips for 1 hour at 400 degrees C. Yes, we have ovens. Okay, so anybody that uses TLDs has ovens, two temperature ovens, and they have a reader and a bunch of chips. Then after you heat the chips for an hour, you heat them at 80 degrees for 24 hours, or so it's either this or the other, or you heat them at 10 minutes after you irradiate them. Either of this removes the peaks of the two lowest temperatures and prevents the trap leakage. So this process right here ensures that you get a nice looking peak like that. Okay. And then you irradiate them. So after you do this, and you do this, usually there's a little holder, there's a metal holder, and all the chips are sitting in there. We used to have 100 chips at a time. So we had a metal holder that had been drilled out with little indentations, and we put a chip in each indentation, and then we cover it with another metal piece, and we seal that up, put it in the ovens. Then we take them out of the ovens, and then we take each chip and put it on a piece of polystyrene that also had indentations. This is very time consuming. And the way you pick up the chip, you can't pick it up with tweezers, because if you take a chip out of the chip, then the response is different. The light output is different, because the volume just changed. So you have to use this vacuum pickup. It's this tiny little tube that has suction, and you just touch the chip and it holds it, and you transfer it. So we transfer it to this polystyrene sheet, and then we irradiate the chips equally on the linac, and then we we read each chip, and each chip has a calibration factor associated with the chip. So we irradiate it with say 200 centigrade, and then we run it through the glow curve, and we get a reading. And by the way, the glow curve, when you integrate the area, it becomes nanocoulombs. It goes from amps to nanocoulombs, because you're multiplying by a time. So then we get chip factors, and then we get a machine calibration factor before we use the chip on the patient. Okay, advantages of TLDs. The ones that most people use are called TLD100. That's just the name they are. They're a particular kind of lithium fluoride. It has a very, very wide useful range. It has from millirad, you can measure from millirads to 1,000 rads, and then it's super linear after that. It's not dependent on dose rate. Okay, so if you're running your machine at 200 ME per minute versus 1,000 ME per minute, it's not going to make a difference. The small size can be placed in cavities and can be used for high resolution dosimetry. So if you put the chips close to each other, you can get better resolution in a chamber, for example. You can reuse them. So we would use them on a patient, and then we would re-anneal them. So we put them in the ovens again. We heat them up again, and then we can reuse them again. The thing is, it's very, very technique based. Okay, so every time you anneal them, and every time you get a chip factor, you got to keep track of the chips and their factors. Okay, so if you've got chips that the factors are fluctuating up and down every time you anneal them, every time it goes, you should probably toss it. Okay, because you don't want that. You want a chip that's always going to keep the same factor. This is all very time consuming, and it's very technique based. Accuracy and precision, 1 to 2% can be achieved. Typically in the clinic, we would get more like 5%. Okay, precision for the chip, which isn't great. Okay, disadvantages of TLDs: lack of uniformity. Each chip has its own factor. The TLD stability can vary over time if low temperature peak exists. So in other words, if you read it right after you radiate, you might get a different reading compared to the next day that you read it. It's sensitive to UV light. That's not that big a deal. Destructive readout, which means that after you read it, say you read it and the computer crashes, you're stuck. Okay, you can't reread it. If you reread it, you won't get a signal because you pulled the electrons out of the trapping sets. And then your reader also. I mean, it depends on how stable your reader is. You're reliant on that. Here's a practical example. We have 2 TLDs. We usually use 2 because we want to take an average. Okay, so 2 TLDs, they're called A and B, are placed together on a patient. And they're usually in these little tiny envelopes. We stick them in the envelope, and they're very close to each other. We put them on a patient, and we treat the patient to 200 centigrade. Then a second set of TLDs, these are the control chips. We always have control chips when we're using TLDs. They're placed in solid water phantom under reference conditions, and they're delivered, and we give 200 centigrade. We give them a known dose. So the control chips are chips that have a known dose. Okay? And the chip calibration factors are as follows: 25.96, 97, 98. And that comes from, remember how we annealed them, then we irradiated them all equally, and we read them out. That's where those chip factors come from. Okay? And by the way, this is not nanocoulombs. These calibration factors have no units. And the reason is because, say you irradiate 100 chips, and you read them all out, and you get numbers, you're going to get numbers like, I don't know, you might get, you get numbers like this, 60 microcoulombs. Okay, so we tabulate all that in Excel, and then we get an average, and then we divide every chip by that average. Okay? So basically we're normalizing all the chips to an average coulomb. That way we get nice numbers like this. We don't have crazy numbers like that. Okay, so and it's a nice factor, and it relates the chips to each other. It's basically, this calibration factor is an intercomparison number between chips. Okay, imagine if you're using 2 chips on a patient, and one responds differently than the other one does. Okay, so you need some numerical way of normalizing them so that you take the dependence out. That's what these are. Okay, so now your readings for A, B, C, D are those many microcoulombs. What is the dose to the patient? Okay, and that's going to be your assignment. And so that's on the assignment. Just to go through this quickly, what you need to do
It's read only, so you can't do that.
Oh yeah, that's right. But I can say that as something else. I can give it another name.
But you have to interrupt the slideshow.
Yeah. Maybe I'll do that. Oh. Escape's not working. Yeah, you're right. So how do you do it? So you take those readings, and first, what you need to do is you need to take reading A. Okay, reading A of chip A. Which ones are the patient chips? A and B. Okay. So reading A divided by the chip factor. I'm going to call it FCF. Okay. Plus reading B divided by CF B. CF B, CF A. Okay. Divided by 2. That's your. So this is going to be average reading. So this is going to be your average. Okay. So what are we going to call this? So this is going to be reading average. Okay, don't add these two first. You gotta divide them by the chip factor, so that's reading average. Okay, so then there's the control chips, and then you take RC over CFC plus RD over CFD over 2. So this is reading control average. Okay. And then you need a factor that converts dose to reading. Okay, and so then we're going to take. Then you're going to say factor. I'm just going to call it factor equals 200 centigrade, because that's our known dose, divided by R control average. Okay, so that's the factor that we can multiply every reading by this factor, and that converts the reading to dose. Okay, and then so dose A. Sorry, dose A. No, dose is equal to. I think I hit that. I'm saying dose is equal to our average times factor. Okay, so that's how you do that. I think that makes sense. All right, divided by 2. Yeah, average control divided by 2. I think that works. Anyway, it's on your assignment. Okay, next one. Optically stimulated. So this is a newer dosimeter. We had a new one? Okay, it might be okay. Optically stimulated dosimeter. This is a newer dosimeter that now, if you guys look at your dosimeters that you wear in the clinic, they have OSLs. The Landauer company uses OSLs. Optically stimulated luminescence. That's a little bit very similar to TLDs in the way they work, but they don't use heat. They use light. Okay, so this is an aluminum oxide crystal, and as you irradiate it, it also traps electrons. But it releases those electrons just by shining light on it. They shine a particular kind of light on it, and those electrons come out and they give off light, and they measure the light, just like we did with TLDs. Let's see. So the advantages, I'll go over the advantages. One major advantage is you can reread them. You can shine light on it and give off light again, which you couldn't do with TLDs. Anyway, they're called nanodots. The Landauer product is called nanodot, and it's stimulated by laser light, and then they give off more light. The dose range is 0.001 to 1500 rad, so that's a nice range for us. Precision as low as 2%, kind of like TLDs, right? Energy dependent, it must be calibrated for each energy. So these are energy dependent, but there is a calibration factor for each energy. Nonlinear response above 300. So this is lower. What was the nonlinear response of TLDs? Where did that nonlinearity begin? What dose level did that begin at? Do you remember? TLD's nonlinearity starts at about 1,000 centigrade for the lithium fluoride 100. Okay, this one starts a little lower, so we need to be a little careful with these. Many radiation badges have these. Non-destructive readout, you can reread it over and over, and I suggest you guys go to these sites. Some of the questions on the assignment are not, the answers are not on these slides, the answers are on those websites. Okay, so this one here is the Landauer website, and then this one down here is a nice talk from AAPM summer school. It's a really nice talk on OSLs. Okay, some more information about OSLDs, optically stimulated light dosimeters. Let's see. The reporting dose, again, there's the range, 10 millirad to 1500 rad. Okay. Linear response up to 300, software supported, nonlinear calibration. So they can, So if you're using software and you've got the characteristic curve for the chip, you can go up to 1500 centigrade because the nonlinearity characteristic curve is in the software. Kind of like the characteristic curve in film, same idea. Energy range, 5 keV, works fine, up to 20 plus MeV, that's good for us, we don't have to worry about that. Accuracy, it looks like 5% for standard and 2% for screen nanodot. The screen, I'm not sure what that means. That probably means that there's some nanodots with some better QA, and then they go through a more rigorous QA, and you can get 2% of those. Minimal dose rate dependence, no temperature dependence, no angular or energy dependence. Ideal for challenging clinical situations. Let's see, what else is important here? One calibration accurately measures dose. Okay. Radio translucent. Okay.
For the OSLs,
Yeah.
are these only used in badges or they're in vivo applications?
They're in vivo. You can order them. You can buy an OSL kit just like you would buy a TLP kit. Okay, they come with many OSLs and they come with a reader. And the reader is actually a lot smaller than the TLP reader.
Is the TLD more popular than like in
OSLs, I believe, are becoming more popular. The reader's smaller. You can reread them. In terms of costs, that's I'm not sure how much they cost. TLDs are really cheap. Back in the day, they're a buck a chip. Okay. But like I said, the TLDs, you've got to really monitor their correction factors because they can change over time. With OSLs, I don't know if there's as much of. I don't have any experience with OSLs. So, but I know that there's a couple of centers around here that use them, and they have their own readers. If you don't want to buy a reader, you can always contact Landau, and they'll send you OSLs. You can use them, and they'll overnight read them for you. Okay, moving on to diodes, another type of dosimeter. Diodes are a semiconductor device. Okay, so TLPs are a crystal, OSLs are aluminum oxide crystal as well. Diodes are semiconductor. Okay, mostly they're made of silicone. They have a high sensitivity due to the high density. So we're comparing that sensitivity to a chamber. A chamber's got air in it. There aren't as many molecules to irradiate. Diodes are solid. They're made of silicone, so they're much higher density than air. And they only require 3.5 eV versus 34 or 33.97 eV in air. So they don't require as much energy. Energy dependence. So there's some energy dependence with diodes. They respond excessively to low energy scatter, such as that encountered in a large photon field. So diodes are typically only spec'd to a field size of like 10 by 10. As your field size gets bigger, you start to and your diode's in the middle of the field, for example. As your field size gets bigger, you're now reading more scatter because you're reading photons that scatter off somewhere else and have enough opportunity to scatter enough times to create low energy photons. So there's a high proportion of low energy photons in larger fields and in smaller fields, and those low energy photons are now increasing the response of the diode more than we want to because of the high Z of silicon. Remember the high Z issue. So typically diodes are used for smaller fields. The diodes can experience radiation damage, so over time diode sensitivity can drop. Silicon has a Z of 14, makes them extra sensitive to low energy photons. Okay, and some of them have a metallic filter. And the metallic filter is there to filter out those low energy photons that are going to increase the sensitivity. Those are called energy compensated diodes. Here's what they look like under X-rays. Okay, you can see the contacts. The sensitive area is right there. It's tiny, really small. Details of diode construction. It was not possible to obtain a radiograph for the QED. Okay, this was some study where they were showing diodes. I got this from this website if you want to go on there. Just so you guys know what they look like under X-ray. Okay, more information. They can be either P-type or N-type. You guys have studied diodes, right? When you're in undergrad. So P-type diodes have impurities added to them, which creates an abundance of holes. And a hole it's basically a trapping center for an electron, right? It's an opening where an electron can drop into. So a P-type semiconductor has a lot of holes, or electron receptors, And these are the most common ones you'll see for radiation dosimetry. N-types produce many electron donors. So you can add certain impurities to create into silicon that creates electron donors rather than electron receptors. Let's see. Radiation damage affects the N-type more than the P-type. Okay. And to prevent that, to reduce that or mitigate that effect, the N-types are usually pre-irradiated with 4,000 gray. Electrons, and once you do that, then they're not as sensitive to radiation damage. Electrons diffuse and are then carried away by electric fields, and the signal is proportional to dose. So the diode is used in connection with an electrometer. So the diode is connected to an electrometer. And as you irradiate it, the radiation, the electron flow, creates current inside the diode. And that current is proportional to dose. They usually operate without a bias to reduce leakage current. Because as you put a bias in a diode, you're going to create a leakage current, and we don't want that. Commonly used as in vivo dosimeters or scanning dosimeters in a water tank for relative dosimetry. So you can either, and I think I have pictures of them. So diodes are used in vivo dosimetry. You can put them on a patient and read them out, or you can use them kind of like a chamber in a scanning tank. So here's a dose rate dependence for N and P type diodes. Look at P type. Isn't that great? Look at that. Dose per pulse. These are 5%. This is a 5% window here. So it's easily within that 5% window. It's pretty flat. Okay, so, and this is the dose per pulse of radiation. But N-type, there is a radiation dose rate dependence for N-type. Okay, so here's just some pictures so you know what they look like. Diode detectors. This comes from the Nuclear website. If you want to get more information, here's a website. They're made in different colors because they respond differently to different energies. Okay, so diodes will respond differently to photons. I think these are the photon diodes, and these are the electron diodes. The energy range. So these colors correspond to certain energy ranges. Okay. So as you go to a different energy, the response will be different. Okay, and so you can go to the website to get more information on that. Now, they're also temperature dependent. So diodes will respond differently at one temperature, and then if it gets warmer in the room, you'll get a different response for the same dose. So why is that a disadvantage? The room is usually 22 degrees C, right? So why is that a problem? The problem is that when you calibrate the diode at 22 degrees C, you get one calibration factor. But then when you put it on a patient, what's the temperature of the patient? 37. Okay. And that difference, 22 to 37, 15 degrees, is enough to cause a different reading, a 15-degree shift. So IBA makes this skin temperature calibration fan. And I think the way it works is you fill this with water of body temperature, and you put the diode on that, and that's what you use to calibrate the diode with when you irradiate it. Come up with your cal factor. See, and it even comes with a little thermometer.
So there's no like standard temperature correction equation?
No, because with chambers, we know that it's proportional to that equation that we use, that KTP equation. As temperature goes up and down, we can just put it in there, and that'll work. It's linear, in other words, with that equation. With we don't know the linearity of the diode, and certain diodes may exhibit certain response for a certain change in temperature, and others the response will change. So the recommendation is that you measure it at your diode, whatever diode you buy, you calibrate it at body temperature. So it's something to watch out for. I mean, these are important things for you guys to know, so that you know when you go out in the clinic and you use these devices, you do need to calibrate body temperature, and they are energy dependent. Some of them are dose rate dependent. So these parameters and these dependencies you need to know about before you use them. The map check, I brought the map check today because it's the device we use almost every day to check IMRT, to do our MRT QA. This device is made with N-type diodes. Okay, they call them sunpoint diodes. The sensitive area of the diode is 0.64 millimeters. They're tiny diodes. And You guys have used this, right, before? And each little dot on there, on the surface, represents the position of the diode. And this is just some information about the MEP check that you should know. The response after accumulated dose. So the response of the diodes in this device changes 0.5% per 1,000 gray for 6 MV, and it changes 1.5% per 1,000 gray for 10 MV. So 10 MV affects it more than 6 MV. This is important to know because if you deliver, say, 2,000 gray in the course of a month, this thing, through all the QA, your diode's response will change 1%, okay, for 6 MV. And that's important to know that. But it's okay that they change their response because this device allows you to recalibrate after a certain time. You can recalibrate anytime you want. Okay, so that gives you an idea of how much that's going to change. So based on that, and based on the typical clinic workload, the manufacturer recommends calibration about once a year. Maybe a little more often than that is better. And the calibration, have we done a calibration? Oh, we did it for the profiler. Remember how we set it up, and then we turned it, and we radiated it, and we turned it, and then we shifted it? That's the calibration process that interrelates the response of all of those diodes to each other. Okay, that's what they recommend to do a little more frequently than once a year to recalibrate the device. So that calibration process compares the diodes with each other, but then there's also the dose calibration, where you deliver a known dose to it, and you tell the software, I've just delivered 200 centigrade, and then it comes up with a calibration factor for the diodes. So there's two calibrations that you do. Okay, dose rate dependence. This is also something that may be considerable. 2%, that's a pretty big number for us. 2%, you'll see a 2% change between 50 and 600 NU per minute. Okay? Most of the time we're treating our patients at 600 NU per minute. But what about IMRT? The dose rate changes as you deliver. I don't know if you folks have noticed when you deliver an IMRT field, the dose rate goes up and down. Okay, and it does drop to 50. It might even drop below 50 in some cases. Okay, so this device will experience shifts that are that big. So what do we do about that? Well, the manufacturer recommends that we calibrate at 160 MU per minute, because really, we're not going to use this for just regular 3D conformal treatments. We're going to use this for IMRT. That's what it's used for. So since we're going to use this for IMRT, we are going to see those differences. So they recommend we calibrate at 160 MU per minute, which is kind of the mid-range. Okay, temperature dependence, you may want to calibrate before each measurement. So again, there is a temperature dependence. So they're recommending that you might want to do that 10 by 10 calibration shot before, not the array shot, because not the calibration where you turn it and shift it, because that calibration that just compares each diode between each other. They recommend doing the 10 by 10 calibration for dose. Okay, so if the temperature is different between days, you're going to take that into consideration when you do that calibration. Okay, some more information about diodes. There's a schematic. Here's a schematic of a diode. So diodes are sensitive to, well, here, let's look at it a little bit. There's the sensitive volume right there. Okay, and there's a copper contact. So this contact comes around and forms part of the cable. And here's the other contact. And this one here has a 2 millimeter depth. Epoxy. So when you see this, all you see is this outer case. Design of an unbiased PN junction. Okay, and that's how you use it in a circuit. There's a diode connected. Remember how we always need an op-amp to increase the signal? So we use an op-amp, which is basically an amplifier, which gives us a higher signal. So diodes. There is some angular dependence that you need to know about. There's energy dependence. We already talked about that. The metal filter flattens the energy response of the diode. There's a temperature dependence. Field size dependence should not be used for larger than 5 by 5, and some of the, depending on the manufacturer, you may be able to go to 10 by 10. Can be used as biased or unbiased. Okay, high response, quick response. If it's biased, you have a high response, but it's much more temperature sensitive. And then you can find more diodes here. This is a report. No, it's a talk. Okay, that's diodes. Any questions about that? Okay. So where do you use them? In vivo patient dosimetry and diodes. I use diodes a lot in when I did my stereotactic beam data collection, because diodes are so tiny, I get really good resolution, so I can scan small fields at very high resolution. Okay. So patient dosimetry, scanning radiation fields, map check devices. Okay, so that's where you see diodes. MOSFET dosimeters. Okay, so MOSFET dosimeters are a little bit smaller than diodes. Diodes are already small enough, but these are actually smaller. They're also temperature dependent, and they're sensitive to bias fluctuations, and can be used with or without bias. So a MOSFET stands for metal oxide silicon semiconductor field effect transistor. In undergrad in electronics, you probably work with FETs, right? Field effect transistors. They're a certain type of transistor. So this is a transistor basically. It's not a diode. So it has three contacts. And this is MOSFETs are typically used for patient in vivo dosimetry. You don't see too many MOSFETs being used for dosimetry purposes, although you can still use them for dosimetry purposes. But they're nice. This is one of the devices that we use at North Shore. This is the reader. This is the bias supply. So this supplies a small bias voltage to the MOSFET. The MOSFET needs a bias, and the way you use it practically is use zero. You tend to use one at a time. You don't use them all like this. So as this is all connected, you zero it by pushing this button here. It zeroes up the MOSFET, and then this is disconnected from the reader, and then you bring this box connected to a diode into the room, okay? And you place that on the patient. And this little part right here kind of looks like this. It's like we call it a bubble. It looks like a little bubble, and we tend to use this. There's less of an angular dependence if you place the bubble side down. So this is the patient's skin. And you want to place the bubble side down because there's less of an angular dependence. If you place the bubble side up, it demonstrates more of an angular dependence. So, which means that you'll get a different response when the gantry is at one angle versus another angle. Okay, so you bring that into the room, you put it on the patient, you tape it on, because they're really small, they can fall off. You irradiate the patient, you come out of the room, plug it in, and you hit the read button. Okay, and it tells you what the dose is. These have all been calibrated. So before you can use this, you need to put them again in a known 10 by 10 field at Dmax or 5cm or whatever, and deliver a known dose. And then after you do that, you read it in this. There's a calibration mode, and you type in the dose that you gave it, and so each one has to be calibrated before you use them. So here's some more examples. This one here is not connected to a bias supply, even though it does need a bias to be read out. But it's a lot smaller, and there's no cables coming out of it. So it looks like that. You can put it on the surface of the patient. There's some copper contacts over here, and there's a little white area where you can write a number if you want to identify it. So after you irradiate it, you come out of the room and you put it in this reader, and that reader has the bias, has a little battery in it. And then you just hit read, and you can actually put the patient's MR number on there. There's a little memory chip. A little bit of memory, you put a patient's MR number, and then it stores the dose. And we used to keep those in the patient's charts. Okay, so, and you can reread that. Okay, so that's non-destructive as well. And this is called one dose. Okay, pros and cons of MOSFETs. MOSFET's dose is permanent. It can be read out offline. In other words, it doesn't need to be connected to a readout system. This means the cables are not required, although some of them do have cables. Dose is reproducible within 3% for doses greater than 20 centigrade. They respond identically to electrons and photons. So remember, with the diodes, you have to have different diodes for different energies. You don't need that with MOSFETs. That's the nice thing about MOSFETs. And their energy dependence is within 5%, which is not great. So you got to watch out for that. They're very small, 0.2 by 0.2 millimeters, and need to be encased and attached to cables. Well, I say I don't need cables, and then I say you need cables. Well, you can get both kinds. Okay, you can get like the one dose that doesn't have a cable, and the other ones that do have a cable. They need to be attached to some form of some way that you could read them. So chips don't need to be attached to cables. They're not being read by any electronics, but these do need to be read by electronics. There's an angular dependence of 2%, and if you guys want more info, you can go here. This is Thomson Electronics. This is the website that makes their MOSFET reader. Website of the company that makes the MOSFET reader. And here's the sensitivity of MOSFETs. So dose range. Now these MOSFETs have a lifetime. Diodes, not checked, you can use it for years and years. We know that the sensitivity changes slightly at 0.5% and 1.5%. These have a much shorter lifetime. At about, if you're using them, there's two sensitivity levels. There's low and there's high. If you're using them in low sensitivity, you can get up to 200 gray out of the lifetime of the MOSFET. If you use it in high sensitivity, you can only get to 74 gray. Okay, so 1/3 of the lifetime in high sensitivity. But high sensitivity gives you more accuracy. So let's look at this table. The accuracy for a dose of 200 centigrade, which is a typical dose we give our patients, is 2% in standard and 0.8%. So it's pretty good sensitivity in high sensitivity. And then for lower doses, the sensitivity drops. You see that? So as your dose gets lower, the sensitivity drops. That's kind of like signal-to-noise ratio. If you give it more signal, you're going to get better sensitivity. I think we use it, primarily we use it as standard because, so standard, and then typically you're not going to deliver all the fields to one MOSFET. Because when you're doing patient dosimetry, you put it on the patient and you deliver one field. Because if you're delivering other fields, they're going to scatter and they're going to interfere with the reading for that one field. So we deliver one field, and then they remove the MOSFET reading. So for one field, we tend to get doses around this range, 100, maybe 80, 90, just typical for the typical doses. So in standard sensitivity, we're looking at about a 3%. And in our clinic, our tolerance for the diodes is it's 5%. That's our tolerance. So this is 3% under ideal conditions, but you've got to throw things in like temperature, angular dependence, and that increases the error. So we have a limit of about 5%, and I would say 99% of the time they pass within 5%. If it's delivered properly and placed on the patient properly. Okay, and this is the sensitivity. So 2.7 millivolts per centigrade is the sensitivity in high mode. And then this is just a schematic of what a MOSFET looks like. And the way it works, the way a MOSFET works, dose is proportional to this delta V. And delta V is the voltage that's required to maintain a certain amount of current through the gate. You know, the MOSFET has a gate, has a source and a drain. Okay, so to maintain a certain current through the gate of the transistor, you need a certain amount of voltage. So as the MOSFET gets irradiated, to maintain that current, because of the radiation damage, you need more and more and more voltage. So when you're zeroing it, what you're doing is you're zeroing it, it's measuring how much voltage it needs to maintain this current. Then you put it on the patient, it experiences some radiation damage, and then you bring it back and you read it, and then what it's doing now is it's comparing the voltage it needed before with the voltage it needs now. That difference in voltage is proportional to the dose the patient just received. That's how that works. Freaky. Okay. Completely different type of dosimeter. Changing gears here. Oh man, we're almost done. Freaky dosimetry. I know I probably raced through this stuff, but I'm recording it. Hopefully you can listen to it again. I will definitely make sure that today's is going to be posted on D2L. Okay, freaky dosimetry. No, freaky, funny sounding word. It's a chemical dosimeter, and the way it works is as you irradiate this stuff, this freaky is this ferrous sulfate. It's made up of ferrous sulfate ions. And as you irradiate it, they become ferric. So they become from 2 plus to 3 plus when you irradiate it. And so the process of dosimetry is measuring how many have been converted to from ferrous to ferric. And the way you measure that is with spectrophotometry. Not everybody has one of those in their clinic. Okay, this is more of a research tool. Okay. So basically what the way spectrophotometry works is measuring the opacity. It's like optical density. You're measuring the opacity of the solution. And the proportion of 3 plus to 2 plus, that proportion depends on the opacity, or the opacity depends on that proportion. So there's this thing called the G value. It's the number of molecules produced, destroyed, or changed by the expenditure of 100 eV of radiation energy. Okay, so for every 100 eV, the G value is going to go up. And the dose to the frequent dosimeter is it's just a simple equation. Delta M comes from the spectral analyzer, so the delta M is proportional to the change in capacity. Rho is the density of the solution, and G is a known value that depends on the type of radiation. Okay? It's kind of like your calibration factor. When I was doing our master's research, there was somebody that was doing her PhD in frequent dosimetry, and so she was doing a lot of research in that. And people still use that. Bang gel dosimeter. So this is a different type of dosimeter. And now polymers are suspended in a gelatin solution. They can be irradiated, and the dose information is determined from an MRI scanner. Okay, so now the MRI is the reader. We're not using an electrometer. We're not using a TLD reader. We're not using a photomultiplier. We're using an MRI to measure dose. So the MRI signal is proportional to dose. Higher signal means more dose. The bang gel dosimeters use either radiochromic dyes or frequent dosimeters. So the MRI can measure how much of the 2 plus to 3 plus has been converted. Now, the MRI signal depends on that. Highly promising. You still see people using this stuff, but it's mostly research labs that have access to MRI units. The beauty of bang gel dosimeter is this my last slide. Okay, the beauty of bang gel dosimeters is that they're 3-dimensional dosimeters. So, most of the dosimetry we do is either point dosimetry or 2D dosimetry with film. But what's nice about bang gel is it gives you 3-dimensional, and you can get 3-dimensional scanning. So, people have used this for stereotactic radiation. So, say you've got a head like a phantom, and you can fill it with bang gel. Okay, and you can put it through a CT scanner and scan it, do a treatment plan on it, a 3-dimensional treatment plan, stereotactic treatment plan, and then you can irradiate this phantom like you would a patient, put in an MRI, and now you're comparing the 3D treatment plan to the 3D MRI image. Okay, so you get tons of information if you can compare it. Rather than what we do now, what I do now when I'm checking my stereotactic dosimetry is I put a little piece of film in a small phantom. But I just have a 2D. That just gives me 2D information. So it doesn't give me the whole picture. So this gives you a lot more information. But you need to know how to use this stuff. You need to be able to buy it, and you need to have an MRI. It's very hard to get time on an MRI because they're expensive and we're scanning patients on them. Okay, calorimetry is the last form. Very rare. I'm not sure who's doing calorimetry, but it's a measurement. Basically, the way it works is it's the measurement in temperature rise, and they relate that temperature rise to dose. Okay. Now, radiation, as it delivers energy to tissue or to material, it's going to increase the temperature of that material very slightly. Okay, but it does increase the temperature of the material because it's imparting energy. It's considered the most direct way of measuring dose because you're measuring energy. It's exactly you're not measuring ions collected and relating them to dose. You're not measuring light collected and relating it to dose. You're measuring energy. You're measuring dose. And so 1 gray is equal to 1 joule per kilogram. We know that. That's just the conversion. 1 calorie is 4.18 joules of energy. So 1 gray is 1 over 4.18 calories per kilogram. So we can convert calories and we can measure calories. The average dose to the calorimeter, and it's a simple formula. Delta T is the temperature rise within the calorimeter, H is the heat capacity of the device, and delta is the thermal defect. The temperature rise is measured with sensitive thermistors, which measure temperature from a change in electrical resistance. You guys ever use thermistors in your undergrad? It's just two metals. I think you just measure their resistance, and temperature affects that resistance. That's how that works, and it's a very accurate way of measuring temperature changes. So that's calorimetry. Of course, the calorimeters are large. They're like big, so you can't put it in a patient. You can't put it in a phantom. They're large. So it's just an accurate way of measuring those directly. Okay. Oh, I can't believe we made it. That's great. Okay, so let's stop it and